this particular problem that was asked, the problem 1, I had set it as problem 1 A and B, but this Wheeland does not allow A and B. So my T is distributed that is 1 and 2. Effectively, the problem uh, can almost be solved with the funda that you had in the first year. Basically, linear algebra problem, because it only concerns calculating the eigenvalues, eigenvectors, and coordinate transformation. This is something that you've done. The additional thing that comes from quantum mechanics is the basic idea that every observable is represented by an operator, and you can only actually observe the eigenvalues of the operator. So the first question where it asks, if an experiment is performed to measure the observable A, what is the value that you can observe, or what is the larger value? Effectively, can be what are the values that can be observed? These are actually the eigenvalues of the matrix. And since we had given it as a Hermitian matrix, you see these are complex conjugate of each other. So these will give rise to real valued observables. So these are the things that you can actually observe. The second part was that a state is given, and you have to find out the probabilities of each of these eigenvalues to be observed. Now that again comes from quantum mechanics, that if something is in a state given by psi, and the eigenvectors corresponding to the first eigenvalue is this, eigenvector corresponding to the second eigenvalue is that, then all you need to do is to take a projection of the state onto the first eigenvector. That will give the probability amplitude of observing the first eigenvalue. Take a projection on the second one, you get the probability amplitude of observing the second eigenvalue, and the probabilities are essentially the mod square of the projections. Projection the probability amplitude. So it is actually very simple. The only complication was that the psi was given in a different basis. And since in solving problem 1, you have already used the basis 1, 2, that means the x coordinate and y coordinate, that is the basis. Therefore, this particular the eigenvalues and eigenvectors have been obtained in this basis, and therefore all you need to do is to change the psi into that particular basis. Now the psi is given in a basis that makes an angle 30 degrees in the counterclockwise direction with this vector. So that then for the psi was the old set of vectors, and you have to change that into the new set of vectors, which are these, right? So you have to turn it in the clockwise direction to get the 1, 2 vector, and accordingly you have to define the U matrix, the transformation matrix, and transform the vector. You know how to do that. So that is all that was there in this problem. The second problem the TAs requested me to deal with was problem 7. Yes. Here, the state is given at time t0. Okay. So at time t0, okay, the state is given at time t0. The potential function is given and things like that, but that really won't really matter, because if this is given, all you need to do is to multiply these positions with their own phase factors, and then calculate the phase factors at time t by 2. That's all. So let me do it here. Your state was given as at t equal to 0. The state was given as your psi x comma 0. It was 3 by 5 psi naught, the ground state, x plus I 4 by 5 psi 1 x. So that was given, right? So at t is equal to 0, the distribution will be the mod psi square is equal to this square plus this square. So it is basically uh, 3 by 5 psi naught x square plus 4 by 5 psi 1 x square. So that is the mod psi square. Now at t is equal to capital T by 2, remember your t is 2 pi by omega naught, and so we can figure out what this actually is. So then your psi x of t by 2 is, then you have to write this 3 by 5 psi naught x times the phase factor e to the power minus I e naught t by h cross plus this is I 4 by 5 psi 1 times e to the power minus I e1 t by h cross. And now we know that, and here I know that E naught is half h cross omega naught, and E1 is 3 half h cross omega naught, right? So we substitute it here, then you get 3 by 5 psi naught x, and then for E1 you just put here, it will give you, and for the t, this will be t by 2. So it will be minus e to the power I. E naught is half h cross omega naught, and t is t by 2, and t by 2 is pi by omega naught. You can see that this is pi by omega naught plus I 4 by 5 psi 1 x e to the power minus I. E1 is t half h cross, sorry, h cross omega naught. This is done, and t is t by 2, which is pi by omega naught. Pi h cross. Pi h cross here. So cancels off, cancels off, cancels off. So what you effectively get is 3 by 5 psi naught e to the power, this is minus I pi by 2 plus I 4 by 5 psi 1 x, this is e to the power minus 3 pi by 2 I. And if you now replace these by their cosine and sine things, then you find that this is equal to minus 1 and this is equal to plus 1, plus I. So minus I plus I. So this is minus I 3 by 5 psi naught x, and this is plus I. So this is minus, already I was there, by 5 psi 1 x. So again, you see that the mod psi square, let's give some space. Sorry. Is again the same thing. It is 3 by 5 psi naught x square plus 4 by 5 psi 1 x square. So actually it does not change. Now this itself was an even function. Square is of course even function. This itself was a odd function, but square is an even function. The even function, it is an even function, and it was an even function, remains an even function, and therefore the probability of finding the particle in the two sides are actually the same. That would be the answer. Okay, let's go to teaching today. And we expected you to write that in your PDF file. So that would be the basis of answering and marking. Okay. In the last class, we learned that, or last few classes, we learned that if there are a couple of particles, then they can form a combined state, and due to the non-distinguishability of the particles, only certain states are permitted. Now, this brings us to the question of entanglement. That's what we'll actually deal with today. This is actually a very simple concept. Entanglement the understanding of entanglement was actually upshot of Einstein-Podolsky-Rosen's paper, in which they had proposed a thought experiment. I have explained that in the last class. But then people did various other experiments and realized that that actually happens. That means there is a state, entangled state, when the observation of one actually makes the other one collapse. That means the two together has a combined state, each one does not. So the entanglement is essentially a situation where the characteristic of entangled state is that the members of the system system of entangled particles do not each have their own quantum states. Their own quantum. So each one does not have their own quantum states, but the system as a whole does have. So the whole system has a state. That means in the thought experiment that Einstein proposed, there are two particles go in two different directions, and I observe it here, and immediately the other one collapses there. The situation is that they individually do not have their states well defined, but the total state is well defined. And you might imagine the total state to be a entangled state or a singular state. Let's consider the singular state, where this is actually S equal to 0 and S equal to 0, that state I'm talking about. And we have already learned that this is 1 by root 2. It is up, down, down, down. Minus here. So that's the singular state. Here you notice that each of these particles, this is a situation where the first particle is in the up state, second particle in the down state, and this one is in a state where the first particle in the down state, second particle in the first state, in the up state, And this whole thing put together is the state of the system, both the particles put together. And this situation essentially means that each of these are possibilities. And if you say observe the one that is in the left hand side uh, at some distance, say 500 kilometers distance, you observe it and you find that that is directed up. That means it has a spin in the z direction plus h cross by 2. Then the other one immediately collapses to a state which is minus h cross by 2, which means that effectively the whole thing has collapsed only to this particular part. First one up, second one down. So from the whole thing, it has collapsed after the observation to this state. So that is a very peculiar thing to happen, because then Einstein assumed that it is necessary for the information to travel from over a large distance instantaneously, which is not allowed by special theory of relativity. Now we know that it actually does not involve an information transmission over a large distance, because the whole thing is a system. So if something happens in a part of the system, the other part it's a whole system. It's not a question of uh, transmission of information over a large distance. So this is a question of non-locality. That means that a system whose state is defined, that can occur over a very large distance. Over a very large distance. So this is something that is very counterintuitive, but still, I would say that happens. So now the point is that this is an entangled state. And similarly, the third of the triplet state, where this was plus, that's also an entangled state, because that cannot be expressed in a form like this. In a form where, okay, the other thing is that the way to define the entangled state is that, let me again write it, in that case it will be easier. By the way, the entanglement does not concern uh, only the spins. The state itself, the psi function itself, can have signatures of entanglement. For example, if you have the psi of the first particle and the psi of the second particle, these two are defined, and this is defined by the position vector, say r1, and this one is defined by the position vector, say r2. Then if the total wave function can be defined as a simple product of these two, it can be defined as a simple product. This is not entangled. Okay, so this is not entangled. But if it has to be given in a form that cannot be expressed as a simple product of the two, for example, we have already come across a state like this. Then it is not a simple product of the two. And this also represents an entangled state. Okay, so if I want to write the sort of the signature of entanglement, you can express it as follows: a wave function or a state vector. State vector is a general representation, because you can represent a psi in terms of the state vector, or in terms you can also define the spin in terms of the state vector. So state vector representing the state of the system of the particles in an integral state. So a wave function or a state vector represents the state of the particles in an integral state. Well, if it cannot be expressed as a product of product of terms, each satisfying find the state of single particle. A single particle. So effectively, all I'm saying is that, be it a question of the state in terms of the wave function or in terms of the spin, if the state of the system cannot be expressed as a simple product of the terms that come from each particle's state, then the system is in an entangled state. And you can see that we have already come across the states like this. You can already come across states like that. So effectively, we already come across the question of entanglement. But the entanglement, this matter itself. Okay, let us understand another character of entangled state, and then we'll move on to the strange parts. The other character is that entanglement is basis independent. It looks the same whichever direction you look at. For example, let's consider the basis up Z. We have already seen that that is represented as 1, 0. And the down Z, it is 0, 1. So that is the basis. And suppose there is a singlet state defined on that basis, and I now want to look at it from another angle. Now, another angle means I need to define things in terms of a different up in some arbitrary angle n, right? And we have already seen that the state vector, the up vector in the arbitrary angle n, can be written as cos theta by 2, and this is e to the power I phi sine theta by 2. We have seen that already. And this can be written in terms of these guys as, say, cos theta by 2. This is up z. If I do not put a subscript, it essentially means that it is up z. Plus e to the power I phi sine theta by 2 down z. Okay. So this is the situation. I have some state given in that form, and I want to express in this basis. So now I also need to write the down one. Down n is, we have already seen this, minus e to the power minus I phi sine theta by 2, and this was cos theta by 2. Okay. And this is again written in this form, minus e to the power minus I phi. This is sine theta by 2 in terms of basis, plus this one is only cos theta by 2 in terms of the down basis. Okay. So therefore, the singlet state in this particular n direction will be written as the singlet state that will be written as 1 by root 2. It is up n, down n, minus down n, up n, right? It is a singlet state in the n direction, any arbitrary direction n at an angle theta with the z-axis. So now we can substitute these in these positions and simplify. So let's quickly do that. So this is 1 by root 2. Then I have to substitute up n, which is this. So this is cos theta by 2 up z plus e to the power I phi sine theta by 2 down. This is this part times. So again this one down z. So this is times minus e to the power I minus I phi sine theta by 2 up plus cos theta by 2 down. Okay, so I have written only this part minus 1 by root 2. I have to put a whole bracket, but just to make things simpler, I put third bracket. Sorry. Then this becomes the down first minus again minus e to the power minus I phi sine theta by 2 up plus cos theta by 2 down times up cos theta by 2 up plus e to the power I phi sine theta by 2 down. Okay, now we simply cross multiply this and you'd see immediately that this term when it couples with there will be term, the cross terms, sine cos terms will actually cancel off. Okay, but the cos terms will remain. So effectively, it will lead to just do this simplification. You can always do that. I just don't want to spend a lot of time on that. So this is 1 by root 2 that comes out up front, and it will be a cos square theta by 2 plus a sine square theta by 2. This whole thing in a bracket, and it will be up and down, up and down. So this one will simplify to that. Huh? So cos square up, down, cos square comes here. This one and this one, sine square, and these two cancel off. Therefore, sine square plus cos square. And when you actually multiply these two, when cos and sine and cos, they will get a they will simply cancel off. In the similar way, this one also leads to minus cos square plus sine square, cos square theta by 2 plus sine square. Again, this one is down, up, down. So this is down 1, 2. It's better to write that way. Down 1, up 2. And this actually are 1. Therefore, we get a very simple result. It is just 1 by root 2 up, down, minus down, up, which is in the z direction. Now, notice that we had started with the singular state. In the end, any arbitrary direction, its form is exactly the same as what we observed in the z direction. This essentially leads to the conclusion that the singlet state is basis independent. I mean, whichever direction you might look from, the singlet state looks the same. That means the spin in the up direction, spin in the down direction remains the same, whichever direction you look, you analyze it. Okay, so this is a very special character of the singlet state, which is the entangled state. Great. So now let us go into a few very peculiar situations that result from entanglement, something that many scientists were very uncomfortable about, and you might count me among them. So it is not that I am trying to convey my comfort with the situation, rather I am trying to convey my discomfort with the situation. Entanglement is actually not very uncommon, very peculiar, special, nothing like that. Whenever particles are there, in many situations they do get entangled. For example, consider the situation that I'll better use the straight line. A light beam comes and that falls on a half silvered mirror oriented at 45 degrees. As a result of that, a part of that will be transmitted and a part of that will be reflected. Okay, so a part of that is transmitted, a part of that is reflected. If you have a detector here, say a detector somewhere here and a detector here, each photon will be detected. So either a photon will be detected here or a photon will be detected there. Right? Now, quantum mechanics demands us to believe that before it is detected, it is not really traveling this way. Before it is detected here, it is not really traveling this way. But what is happening is that the photon is in a superposed state of either being transmitted or being reflected. There are two possibilities. In that case, somebody in quantum mechanics will say that if it is transmitted, there are two possibilities. Either it is transmitted, so the possibility is 1 in the transmitted stage, or the 0 in the transmitted stage, which means that it did not get transmitted. And here also you have 1 in the reflected state or 0 in the reflected state. But before they're actually observed, or some kind of a counter is here that clicks, you never know which is true. And therefore, the one that comes out of this beam splitter. So let us call it simply as the beam splitter after the beam splitter. That state should have to be written as some coefficient A times 0 reflected, 1 transmitted, and another amplitude B times 0 transmitted, 1 reflected. So you see, the individual states of the photons cannot now be written as a product of the individual states, and therefore this is also an entangled state. That means the photon emits, photon is emitted out of this in two possible states, and these two possibilities are entangled with each other. And ultimately, when you observe it, the other one collapses. That means if you have observed it and you find it has come here, this one clicks, which means that this is true. So this is true means this is true. Therefore, the other one also becomes 0. Therefore, this is true. And only this is actualized. This one disappears. So it was actually after it was emitted, it was in this whole state. And when it has been observed, it collapses to this state. Now, you might think that how big are these branches? They might be as big as you want. You might place one blimp splitter in Kolkata, this one is in Delhi, this one is in Singapore, it's possible. And then when you make the observation in Delhi, the photon in the Singapore collapses. So again, exactly the same situation as the Einstein's proposed experiment, right? Rather peculiar, but that is what we need to believe if the formalism of quantum mechanics turns out to be true. Let's consider another situation. Suppose in the universe somewhere there is a uranium nucleus, and that disintegrates by emitting an alpha particle. So a uranium nucleus was here. Sorry. Uranium nucleus was somewhere here, and this guy disintegrates, emitting an alpha particle. The question is, in which direction will the alpha particle go? Well, there is no preferred direction. It could go in any possible direction, and therefore it actually does not go in any particular direction. So it actually is not anywhere until you observe it. And suppose you have some kind of a observer here, and you have observed it. The moment you observe it, you know that it actually went in this direction. If you don't observe it, you do not know. And if you do not know, then it is actually in a superposition of all possibilities around it. Okay. Now the peculiarity does not end here. It's even more peculiar. See, the uranium nucleus did not have a net momentum, suppose, when it was before the breakdown, which means that when the alpha particles emitted with a momentum, the other guy, the remaining particle, remaining nucleus, has to have a recoil of exactly the opposite momentum. Then only the total momentum will be conserved. Now, you do not know in which direction the alpha particle went, and therefore you do not know which direction it recoiled. So the moment the alpha particle was detected by some kind of a detector, or you might imagine that there are other atoms or other particles in the universe, and therefore when the alpha particle goes in a particular direction, it interacts with something, and then this guy knows that it has come in this particular direction. The wave function collapses. Only then will the remaining nucleus know in which direction to recoil. You understand the difficulty? Only then the remaining nucleus will know in which direction to recoil, and therefore when it recoils, it also is in a superimposed state of all possibilities, all possible directions of recoil. And only when the other guy has collapsed, its wave function has collapsed, then this guy's wave function also collapses. So therefore, when the emission happened, then the remaining nucleus and the emitted alpha particles, they are in entangled state. Their individual states cannot be defined. But the total thing can be defined in the sense that the total angular momentum is known, is 0. And only if one is observed, the other's state becomes defined. It's a very peculiar situation, but this is what quantum mechanics tells us. These are somewhat difficult to digest, and that's exactly why many scientists, including Einstein, Schrödinger, de Broglie, Planck, they all tried to formulate some kind of alternative quantum mechanics, which ultimately did not succeed. So that still remains an open question, whether we accept this kind of interpretation, or there can be some alternative interpretation. As yet, we do not have an answer. So as yet, all books tell about this particular interpretation, that the state of the particle is undefined unless it is observed. What I was talking about so far regarding the collective states of particles, the boson states, the fermion states, and the entangled conditions of particles. These, and some of these tests concern entanglement. But actually, the experiments have been done with photons, not with electrons. And so I'll need to talk a bit about the quantum mechanics of photons. You earlier had a course on waves and optics, in which you have learned that light is explained in terms of the wave picture of light, in which you have learned that, say, there is a y direction in which the light travels, and there is a x direction here, and there is a z direction out there, badly drawn, but nevertheless. And you know that there is a plane in which the electric field oscillates, something like this. I'm drawing it in the z y plane, and there's another direction x y plane in which the magnetic field oscillates. This is the picture you have got in waves and optics. Is that right? Yeah. So this is the z-axis. So this is the orientation of the electric field, E, and this is the orientation of the magnetic field. And then with that kind of a picture, we have been able to explain most of the features of light, including interference, diffraction, whatnot. And when the particle picture, photon picture of light came, all these had to be explained again in terms of a particle picture. And as you know, that all these were explained in terms of the wave function, interference between wave functions, and the fact that wave function is a complex valued quantity and things like that. You know that. But what about polarization? Polarization depends on this orientation of this plane, and therefore the polarization is something that would be somewhat difficult to explain using the photon picture, the particle picture. But let us first try to recall what we knew about polarization. Suppose there is an incandescent lamp. So incandescent lamp, it is like a its light that is emitted is not polarized, which means that it contains all possible directions of orientation of this electric field. But then if you use a polarizing filter here, then what goes out will be polarized. That means it will not allow the other directions to go through, and it will be effectively, it is a collection of all possible possibilities, but only the one that is up in this direction will go. So it will become polarized. Polarized in the up direction, for example. Suppose it's polarized in this direction. I have to do the up and down both, because if something is oscillating up and down, something is oscillating down and up, makes no difference, and therefore it is basically polarized in this vertical direction. I cannot say it is up or down. And then if you make it pass through another polarizer that is oriented in the same direction, up and down, then it will completely go through. But if this polarizer is oriented in some other direction, say like this, then only a part of it will go through, and that is given by the cos square theta rule. And if it is oriented at horizontal direction, then theta is 90 degrees and cos theta is 0, therefore nothing will pass. So the cos square theta actually it's called the Melas law. That law effectively captures the phenomenon of uh, uh, this polarization. So effectively what I said was that it can be polarized in one direction, and then if it is allowed to pass through another polarizer, then depending on the angle of this polarizer with respect to the angle of this polarizer, and that angle is theta, it will either allow the whole of the light to pass or none of the light to pass or anything in between. All those possibilities exist. The question is how to represent that with the uh, particle picture. The particle picture, it is represented in terms of the spin of the photon. Now, the spin of the photon, uh, then we will be able to represent the state after this any particular state in terms of the whole quantum mechanics basis itself on that in terms of some basis. And you can see that if I have a vertically polarizing filter, it polarizes something in the vertical direction so that anything in the vertical direction will be always pass through. Therefore, the vertical polarization can be seen as a basis state V. Similarly, if we have a horizontal polarizer, that will also form another basis state H. So we have two possible basis states in the sense that if you allow light to pass through first one so that it is oriented in the V direction, if you allow it to pass to another V oriented, then it will the result is unity, which means the projection of V on V is 1. Okay, and the projection of V uh, the, the position H on V is 0, because if you first polarize it in the horizontal direction and then you let it pass through a vertically polarized filter, then nothing comes out. So this effectively lets us to define the basis on the basis of which any arbitrary state is given, and then any arbitrary state, say general, can be defined as some number A times the horizontal plus another number B times vertical, where A and B only have the constraint that mod A square plus mod B square B square is equal to 1. This is a requirement because ultimately it has to be normalized. So then any arbitrarily polarized uh, light can be represented in a representation like this. And then if say in a particular theta direction, if it is polarized, then we can write V in direction theta, vertically polarized in the theta direction, then that will have components cos theta. A will be cos theta times V plus sine theta times H. So any particular direction oriented V in a particular direction can then be represented in terms of the vertically polarized condition and the horizontal polarity condition, these two taken as the basis vectors. What will then be the horizontal in theta? Horizontally polarized in the theta direction, any arbitrary direction, that will be the same as vertically polarized in theta plus pi by 2 direction. Same thing. So this is nothing but, this is nothing but vertical polarization in a direction that is theta plus pi by 2, theta plus pi by 2. Okay. And if we can now write it in terms of that, it will become cos theta plus pi by 2 V plus sine theta plus pi by 2 H. So there are two possible ways of polarization. This is quite in difference from what we learned in case of the electrons. In electrons, the vertical direction has two possible uh, uh, spin magnitudes, plus h cross by 2 minus h cross by 2. But in this case, a situation is that it is propagating in the y direction, and in that direction, if we measure the spin, we can have two possible values of spin, plus h cross and minus h cross. So if it is vertical polarized, its magnitude is plus h cross, and if it is horizontally polarized, magnitude minus h cross, and so on and so forth. And any spin orientation can be analyzed this way. So we have, if we just write it down, it becomes minus sine theta p plus this one is cos theta h. So this is the horizontal component, this is the vertical component. So we can express the polarization in any arbitrary direction, any arbitrary theta direction. Theta is in the angle with a z coordinate, in terms of the vertical and the horizontal. Okay.
Excuse me,
Now,
sir.
yes,
Sir, can you please explain the setup? This V theta and H theta again. What
I couldn't
do
hear
we,
the question. Repeat that again.
what does V theta and H theta represent? Can you clear the setup again?
Okay. Essentially, what we are talking about is that we have let me delete and draw it properly, then it will be clearer. What I mean to say is, now we are considering a polarizer that is oriented at an angle, and the angle with the vertical direction is theta. Okay, so now it is oriented in this direction. So a uh, it will produce uh, a oriented vector. That means it will produce a photon that is whose polarization is oriented this way, right, at the angle theta. So v theta is this one, that can be expressed as a linear combination of the horizontal and the vertical, which is this. Okay. And if it is, if we want to talk about the horizontal polarization in this direction, if we had made a horizontal polarizer here in this direction, then that will result in a state like this. So everything we are expressing in terms of the vertical and the horizontal. Okay. So vertical in the direction of theta, horizontal in the direction of theta. Is that clear now? Okay, now we are essentially trying to find out the probability amplitude. So the probability amplitude the amplitude of a general, we have defined a general thing, general that has a probability of being transmitted or being blocked. Okay, so if it is a general state which is oriented in any particular direction, say a theta direction with a, now we are trying to figure out if it passes through a vertical polarizer, then how much will be transmitted and how much will be blocked. So obviously, what we need to do then, uh, of to be transmitted through a polarizer oriented in this direction. So what we are trying to do is, here we have something that is polarized in this direction, which is at an angle z. So this is that is what goes. But now we have a polarizer that is oriented at an angle z. So this is a z polarizer. How much will pass? If you want to figure that out, obviously we will have to take a projection of this vector, whatever comes out of this polarizer, onto this vector. Okay. So the standard formulation of quantum mechanics, and therefore what we actually need to do is we have to take a projection like this. This is the v theta, that means vertical oriented in the direction of theta, its projection on the vertical orientation in the z direction. Okay, so that is what we need to find out, and that if you want to find that out, then it is v, and we know what v theta is, so we write down it is cos theta. V theta was here, cos theta p plus sin theta h is equal to cos theta comes forward, v plus sin theta v h, and we know that this is 0 and this is 1, and therefore this is equal to cos theta. If this is the probability amplitude, then the probability is probability is this is equal to cos square theta. So that retrieves the cos square theta rule, and so whatever was the experimental observation, the formulation that we have just created has been able to satisfy that. So this is how we represent spin of a photon. Photon has a spin, and its spin in the direction of propagation of the light is either plus h cross or minus h cross, and in that sense it has spin 1. We say that it is a spin 1. And of course, if it has a spin either plus h cross or minus h cross, and it hits something else, then that something else will have additionally that either plus h cross or minus h cross spin. So it will absorb that photon and will acquire the spin. So this is something that is experimentally tested. So we have a situation where h cross and minus h cross are two possibilities in the vertical direction and the horizontal direction. Now you might ask that in our waves and optics course, we have also learned about circular polarization. What about that? Now, circular polarization in our classical picture is where the angle at which the electric field is oriented. In case of vertical polarization, that is a particular plane. In case of horizontal polarization, it is another particular plane. But if it is a particular plane, that plane rotates. So it rotates, and obviously it can rotate either clockwise or counterclockwise. So it is either a right-handed orientation or a left-handed orientation. So there are two possibilities. How do you represent that as in terms of the picture that we are now painting? Well, that is actually ingrained by the possibility that this A and B can be complex numbers. So actually, the circular polarization is represented by the horizontal plus I vertical. So this kind of situation is, or plus minus I would say, because there are two possibilities. And if you want to add this, then you have to also normalize that by putting a minus 1 by 2, 1 by 2 here. So this is the way we represent the circular polarized state. So you might ask, what is the right circular and left circular? So let me write the right-handed polarization, that is represented by So I will write R, right-handed polarized state, is minus half, sorry, it is H plus I P, and the left-handed polarization. So essentially, by using complex numbers here, we can represent all possible states of polarization. Left-handed polarization is sorry, 1 by root 2. It is 1 by root 2. Then it will be minus. So H minus. So these are the ways we can represent the right-handed and left-handed polarization, and everything that you learned regarding right-handed, left-handed can be explained by this mechanism. And if it is a right angular polarization, then in the direction of its propagation, the angular momentum is, so in this case, the angular momentum is minus h cross, and this case the angular momentum is plus. So there are two possibilities in this case. Here,